Express 1 over p times 5 minus p in partial fractions. A team of conservationists is studying the population of meerkats on a nature reserve. The population is modelled by the differential equation dp dt is equal to 1 over 15 times p times 5 minus p for t greater than 0 equal to 0, where p is in thousands is the population of meerkats and t is the time measured in years since the study began. Given that when t equals 0, p equals 1, solve the differential equation, giving your answer in the form mentioned here, where a, b and c are integers. C. Show that the population cannot exceed 5,000. So let's have a look at this then. Here's the question in summary form. Okay, partial fractions first then. 1 over p, 5 minus p. So 1 over p, 5 minus p, linear factors will be a over p plus b over 5 minus p. Multiply through by the denominator both sides then. 1 on the left will be a, 5 minus p, plus bp. Just cross multiply, and then the denominator we're multiplying through by. So here, put in p equals 0. P equals 0. What do we get? 1 equals 5a. And p is 0, so this is 0, so a is 1/5. And if we put p equals 5 now, see what we get there. This will now be 0, we'll get 5b equals 1. So b is equal to 1/5 also, isn't it? Okay, so both a and b are 1/5. So now this equals then 1 over 5p plus 1 over 5 minus p. Okay, so I put the answer up here just to save little room. Okay, so solve this differential equation then. So here, let's do that then. So let's just copy that and move it down, and then we'll separate the variables and integrate. So let's do that then. So I'm going to move this down now and work on this problem. So this will be part B now. Separating the variables. The variables and integrating gives. So let's see what we get then. We'll get 15 come up on this side to be with the dp, so let's put that up there. We'll get the p 5 minus p over here when we bring that down, and then we can simply just move the dt up to be up with the 1, say, and the dp we can leave as is. Separate the variables then and integrating. So on the left we can now replace the 1 over this by these terms here. So it would be equal to, so this tells us then, so it's 15 over 5p plus 15, isn't it, over 5 minus p times 5 dp. Remember, let's just remind ourselves what that partial fraction was. 1 over this was 1 over 5p and 1 over 5 times this. So I've put them both in, but it's 15 times both of them. 1 over 5p, 1 over 5 times this. Okay, well 15 over 5 is 3, isn't it? So we can do that straight away. So this equals, this will be 3 over p, which is 3 ln p. This is 3, it's ln 5 minus p. It's a function of a function, 1 over something, multiplied by the something differentiated. Minus comes out, so we're going to need a minus here, because it's just a minus that comes out to make it a plus, which is what we want, and we need 3 lots of. So that's equal to then, so we'll have 3 ln, minus you divide top divided by bottom, and this is equal to, and this integral here is t plus the constant of integration. So that's the solution then, the general solution. Okay, so now given t equals 0 when p is 1, so t equals 0, p equals 1 gives, see what we get then, we'll get 3 ln 1 over 5 minus 1 over 4, 3 log quarter is equal to k, because t will be 0. So we can now write the solution then. So 3 ln of p over 5 minus p. Now this k is 3 log quarter. I'm going to move that over to be minus 3 ln quarter. And that will equal t, won't it? So this can be changed to a, I'm going to do this as is here. This can change to a plus if I invert this to 4 using properties of logs. So what have we got then? We've got ln of plus u times, so it would be 4p over 5 minus p. And the 3 I brought outside the bracket I'm going to put under the t over here. Okay, so let's unwrap the log then. So that the e comes down, hits this in the air, so 4p over 5 minus p is equal to e to the t over 3. Now I'm going to put the rest of the work up here. So I'm running out of room. So let me just put it in up here. Okay. So 4p then will equal 5 minus p times e to the t over 3. Move this over to be with the 4, so we'll get 4 plus e to the t over 3. Lots of p. So 4 plus p lots of e t equals 5 e to the t over 3. Now p will then equal 5 e to the t over 3 over 4 plus e to the t over 3. So let's see what we want to write it in the form of then. A, B and C. So let's divide top and bottom then by e to the t over 3. So it's 5. Write this term first, 1 plus 4 e to the minus t over 3. A, B, C. A, B, C. So A, B, A is 5. A equals 5, B equals 1, C equals 4. Just to note that, there's the answer. Okay, so why does this hence show that P is always less than 5,000? So basically, we've got this equation here, and I'm going to give myself some room now just to work on it. So I'll just scratch this lot here now, because we've worked on that problem. And I'm going to just look at this equation now. Let's get rid of this. Okay, so we got this equation here. So this is the last part of the problem. 5 over 1 plus 4 e to the minus t over 3. E to the minus t over 3 tends to, as t increases, tends to 0 as t increases to infinity. So its biggest value, this exponential value, if I just draw the curve, here it is here, t is greater than or equal to 0, and it goes forwards. So this value here is going to be 1. Yeah, when t is 0, e to the 0 is 1, so that's 1, and then it diminishes in value. So this will be, p is biggest, p increases rather, I'll write that way. P increases as t increases. So P is equal to 5 over 1 plus 4 e to the minus t over 3, which is always going to be less than or equal to 5 over 1, because this tends to 0. 4 times 0 is tending to 0. 5 over 1 equals 5, i.e. p is less than or equal to 5,000 population.